Okay, so today's the recording for 10/8. As you know, I'm out of town. We're going to talk about interaction instruction structural models. These we've kind of seen already to some extent. We're just going to go over them a little bit more, but we should have seen all of these. So this should not be that new for you. But if it is, if there's something odd about this, please let me know via email. Um, it's very important. Um, I'm gonna turn off the video. There's no reason to have the video there. Um, but let me know. All right, so we're going to discuss interaction models, including purpose, types, and their importance in modeling including use cases. Interaction models are largely designed to explain interaction, how and what interacts with what, right? You typically have two parts, two things, and they're going to interact in some way, and this is what you're trying to model so that you can be very clear about what you're modeling. We're going to talk about other interaction models, including sequence and communication diagrams. Those are much more common once we're further on in the development process. But these interaction models, sequence, and communication diagrams can help illuminate various details in the requirements phase if that's necessary as well, depending on the level of detail. But they are definitely used in the design process. Then we're going to talk about structural models, including purpose, types, and class diagrams. Structural models are designed by design to show us how to actually put the system together. So structural models are almost always used to describe system design. And you've seen class diagrams, hopefully, pretty basic diagrams, right? With three major areas. One is the class name, one is the methods, and one is the attributes. Pretty simple. We're going to actually connect those together with some more complicated ones, and we'll talk a little bit about association, classes, generalization, and aggregate relationships. Aggregate relationships will be probably the more interesting facet of this, but you should have seen at this point, having taken 150 and 250, you should have seen structural diagrams in toto. In other words, you should have seen all this before. None of this should be new to you. We've talked about use cases. We've talked about sequence and communication diagrams. So now we're going to go into a little bit more detail on those. Modeling user interaction or interaction between two things is very important as it helps to identify user requirements. So typically when we're thinking about what the user is going to do with the system, what services we're going to provide and how we're going to provide those services, we need to think about what data goes in and out. We need to think about that interaction. We can also model system to system interaction, highlights communication problems that may arise. One of the key things we think about user interaction and system interaction is they need to interact to get some work done, sure. But what data needs to come in, what data needs to come out, and so forth is really kind of what you're trying to identify here. When we think about, say, an ATM process, we need to have an account number and we need to have a way of identifying ourselves via account number, right? We can do that via the card. The card typically has an account associated with it. Bing, bang, boom. How do we identify that we're the right people with the right card? We usually use a PIN number or something along those lines, right? That is how, when we think about the interaction, we think about how it works, what information is needed where, it allows us to get a firmer idea of what we're looking at. It also makes it easier to communicate with the user about this, this, and this. This is what we need here. This is what we need here. No, we don't use this here. We use it there. That's very useful information to find out in the requirements phase. Modeling component interaction, from a high level view, not just a system, not just a single class or single thing. When we think about components, which is groups of related software, like a system of systems, this would be one of the systems that communicates with another system. Modeling this type of interaction helps us understand if a proposed system structure is likely to deliver what we're looking for. Remember, when we get to a higher level, we get system of systems, so we can have one system and another system, and modeling that interaction gives us a very good view if we have the information we need and they're communicating across. Are we making sure that only the information that needs to be in one area is in one area? So we can look at security as well. All these type of things allow us to look at that. And that's why we model system or component interaction. Because at this level, we're looking at where's the data going, where's the data come from, who has access to which data, because usually system of systems, we might not be in control of all the components. And so we start to think about those. We also start to think about speed, right? When you have a lot of components that have to interact over, say, a network or a smaller interface or whatever, is it going to be, fast enough? Is it going to be doing the things we need to do? Can we make this, can we scale this up? Can we get the dependability we need and so forth? Use case diagrams and sequence diagrams can be used for interaction modeling. You notice I don't say communication diagrams. We're going to talk about that in more detail later on, but essentially sequence diagrams and communication diagrams are equivalent. So if you can use the sequence diagram, you can use a communication diagram. Use cases were developed originally to support requirements elicitation, and it's now incorporated into UML. We used to use so often that it's incorporated into UML. Each use case represents a discrete task that involves external interaction with a system. You go, wait, what? Use cases are primarily user and the system. You're modeling the user interacting with the system. Each use case should represent a discrete task that the system uses, or that the user uses the system for. That's what I meant to say, right? We are modeling the system in the use case. Anything external is what we think of as an actor. Actor is in a use case, maybe people or other systems, but they are external to what we're talking about. We typically represent diagrammatically to provide an overview of the use case in a more detailed textual form, but ultimately, a simple one may be an ATM user. You see the people drawn. This is an actor. And usually, typically under an actor, we have the textual identification of what actor is. And then we draw an arrow from that to use case. And this use case identifies that the user wants to withdraw money. So they're simple high-level view of a withdraw money process. Yay! Tabular description of the same use case. We're going to identify the various things. ATM user is the actor. Description of customer want to withdraw money from the ATM. What data is involved? We're going to need to deal with the customer balance, money. One thing that you're not seeing here is, yes, we have a customer balance, but we also must have an ATM user ID, right? We must identify themselves. We probably also need them to identify themselves as the right person. So we have card, which provides an ID, which we have also a PIN number, which identifies that they have the right? So those type of things. We can break this down by getting a tabular description of the use case and breaking it down and say, oh, we need this. Oh, we need that. What's stimulus? It's a command issued by the user at the ATM. Oh, that's why they don't have the identification of the user or the identification of the PIN number, because this is you're already into the system. You've already logged into the system. This is now a case in which you're already logged in and you can withdraw money. So the stimulus identifies what kicks off the process. And then in response, money spews forth in the ATM. Comments: the customer must have a valid account and sufficient funds in order to do what they want to do. Now, this money, when we talk about the data, this implies how much money they actually want. So some use cases, we can put more use cases in here, and you can see withdraw money, get balance, deposit money. So the user logs in, and these are what they have access to once they're logged in. They can withdraw the money, they can get their balance, they can deposit a check, for instance. And then another customer over here probably refills money. This customer is likely the ATM repair guy or the bank that is going to refill it, but we see it as a customer. This should really not be customer. This should really be listing as a bank employee, as an example. Here's another use case. This one shows many different use cases at once. So the caterer and the conference chair, they can plan catering together. The conference chair, when we think about academic conferences, somebody's in charge, and that's the conference chair. So the conference chair is going to plan catering. So what's going to happen in the planned catering? The caterer and the conference chair are going to talk about what options there are and how much the options will cost. And then at some level, they agree on that, and that is how that gets produced. Yay! So then the conference chair then arranges speakers. He may arrange a keynote speaker or just regular speakers. Keynote speaker is a subset of speaker. As you can see, that's what the arrow drawn there is to show. That speaker is, he's arranging the people that are going to speak, and some of those people are going to be keynote speakers. They're just a special case of a speaker. Now, in arranging the speaker, you see there's an include. We need to reserve a room. Who do we need to talk to reserve a room? The hotel reservations. Yay! Now, a participant wants to register for the conference. They also have to reserve their spot via the hotel reservations process. If they need to language translation, they need to do that via the registered conference process. As you can see, that's included in there. Ta-da! That is a use case diagram. Note, there are several use cases in this diagram with 3 high-level ones and a lower level like participatory one. What do you mean high level? The conference chair sets up the planned catering. They need a caterer to help them. So that primary is the conference chair. And they're going to work with the caterer for planned catering. The arranging a speaker, conference chairs and the speakers are involved. Yes? Conference chair kicks that off. He's going to actually invite a whole bunch of people to present at his conference. Now, part of that is he has to reserve a room. So that's going to do that through the hotel reservations area, but that is included in the arranged speaker. That is not on its own something we do. Then finally, participants that want to register for a conference. They need to reserve a room as part of that, so they need to get the hotel reservations, but the primaries are the planned catering, arranged speaker, and register for conferences. But you can draw more than one use case, as you see here in one diagram. Okay, you can, but be aware that it's multiple use cases. You are, in fact, this one is drawing 4 different use cases, and it's identifying the different things that you can do once you're logged in. Sequence diagrams are also part of the UML and used to model the interactions between actors and the objects within a system. Now, sequence diagram does not need to be an external person. It can be, but a sequence diagram can be parts of the system communicating with different parts of the system, just showing the sequence. For instance, maybe you have 2 objects as an example. Sequence diagrams frequently are used to do that. Sequence diagram shows the sequence of interactions that take place during a particular use case or use case instance. We're going to talk about that in detail in a minute. The objects and actors involved are listed along the top of the diagram with a dotted line drawn vertically from these. Interactions between objects are indicated by arrows. The arrows have annotations which identify what's actually happening. Note a couple of things about the arrows. We do expect 2 things from our downward focused, not from about our arrows, about our diagram. As you can see, these are 4 different objects that are across the top. Ta-da! These could be systems, right? The student system, the new student user interface is an example, right? Whatever. The dorm program, whatever. But I do want to talk a little bit about these lines. So everything involving the program, as you can see, is in this dotted line, and then you see this bracket. This bracket is where it is alive. It is alive for this instance. We need the program during this phase. That's what we're saying. As you can see, the new student interface is probably what the interface that the user actually uses to interact with the system, right? You usually see that in a user interface. So we see the initialize. It initializes the student, then gives you a student number. Yay! Then you go to the select dorm process. You select the dorm. It gives you a dorm room. Then you select the program, and it returns a program advisor for that program. And then when it's finished, student complete, you have a student object. Yay! Okay. Why do we need this? Well, this allows us to see what information we need. When we go to initialize, we probably don't need any information. We have a student number, great. When we go to select the dorm, we're probably going to need the student information. What student information are we going to need in order to select a dorm? This is where we can start to break it down in terms of what data is needed and where and why it's needed there. Are we sure this is the right order of processes and so forth? It's pretty simple though. We create a student, we select a dorm, we select a program, then we're finished. Can we select the program before the dorm? Yeah, why not? The caveat is you don't want to end up with situations where you have all the computer science students in one area and all the art majors in a different area, as an example. So you probably want to set up the dorm first. Okay, but it doesn't matter, right? If that mattered to the system to do it the other way around, then you'd be able to see that and you'd be able to communicate that fairly quickly. And that's what we see. Um, a sequence diagram being primarily used for. You note also at the end of the interaction, you have these X's. That doesn't mean we destroy these objects or anything like that. It just indicates it's no longer interesting to us for this purpose of this diagram. Remember, diagrams are specifically designed to show you something. This one shows you the system of interaction. So the new system interface initializes student, then it communicates with the dorm to select a dorm, gets a dorm room, communicates with the program system to select a program, returns a programming advisor, and then it finalizes its student with it complete. And that's what it's showing. There's no need to show anything else. That doesn't mean we destroy these objects. That doesn't mean this only reason that's shown is so that we know where it's active and where it's alive. Yes? A couple other things, this dorm system might actually, and this program system might actually be objects that we might have to communicate across an API, or it could be a network service that we actually have to communicate with remotely. That's not shown in the sequence diagram, and it shouldn't be. It should only show you what sequence of interactions need to happen. Another sequence diagram, one I like a little better. So we have a customer. This is an external customer. You can see that this customer is external. We might have a system where we have a user interface, and we might have a system that looks like this. This is essentially the customer interface. We're going to phone pizza, right? And the representative object is going to communicate with the customer to get the order. And you can see there's a loop there, okay? But once we get the order, the representative is going to go ahead and get the payment method. And it's going to return a payment method. Now, you'll notice a couple things. One, every time this returns, it returns something, right? This is not obvious, but yes, get order is going to return an order. Get payment method is going to return a payment method. Yes? It's obvious because of the process by which, get order when we're going to get an order, right? So that's your basic idea. So we don't always have to include it. For instance, if this was get a student number and it returned a student number, you probably wouldn't need to write return student number there. Anyway, get payment method, we have two options, and you can see them in brackets. It's in a square bracket. So the credit card company, if it's by credit card, we're gonna register a transaction. Once we register a transaction, it's been considered paid. So we're gonna have confirmed. So we're gonna go ahead to the store and we're gonna go ahead and create the pizza. If the customer's payment method was pay by cash, we'll still put in the order, and the store is going to go ahead and create the pizza, get the pizza, and it's going to create the pizza via the chef. Pizza is going to go back to the store. Pizza is going to be it's going to be ready. Then once it's signaled ready, the store is going to actually send it to the driver for delivery, and the delivery is going to happen. And then they get your pizza, right? Basic idea. Now, again, we don't know how these things actually work. We're looking at objects or things in the system. This could be a remote system. The credit card company could be a remote system. The store could be a remote store, right? Part of the order, what do we need for an order? Well, we need, the pizza you're going to order, but we also need what your zip code is to figure out which store maybe, right? Those are things we can actually work in terms of what data we need. For instance, create pizza. What does a chef need to know in order to create the pizza? Well, when we think about the order, if you order a pepperoni pizza, that's all a large pepperoni pizza. That's all the chef needs to know in order to create your pizza. Done. Now, this mechanism is all delivery. What if you had a situation where you had a pizza place like Coal Fire on Southport? You can eat in the store or they can pick up or deliver, right? We might have another process for which the chef needs to know whether it's an in-store or takeaway. If it's in-store, then we're not going to put it in a pizza box. We're going to, put it on a little nice display pan and bring it to your table. Or tell the waiter to bring it to your table. If it's going to be a takeaway, either delivery or takeout, it's going to go in a pizza box as an example. So the chef might need to know that. The driver needs to know which pizzas go to which house. Pretty simple, but that's how we break down and get the data that we need in order for these sequence diagrams to work. How is this going to give us the sequence? If this sequence happens like this, is this going to give us the operations that are going to yield the correct operation of what we're talking about, right? And that's what a sequence diagrams are designed to do. It's also helpful to illuminate things like, what do we actually need here? What do we need? What does credit card company need? Credit card company needs a credit card, a CVV, that's the 3-digit code, expiration date, and the amount, right? And the vendor, right? And it doesn't need much more than that, and so forth. So we can actually communicate what our needs are at each individual stop along the way as well, which is why we're doing this process. Another one, this is a medical receptionist. This is another way of showing, I'm trying to think of the way, options, apologize. Alt implies, as you saw here, you have pay by credit card or you have confirmed or pay by cash. This is one way to do it. Okay, absolutely one way to do it. Another way to do it is to put it in brackets and then dash lines in between them. And you have authorization okay and authorization fail. So you go to view info, the patient info system. We generate a report from Medcare DB. We authorization server, we're going to contact the authorization server and we get our authorization back. If authorization is okay inside this lane here, we return the patient info. If operations fail, we say error, no access, as an example. So that's just another way to do it. Because remember, a sequence diagram, a use case diagram, and so forth are all designed to show a sequence of interactions. So as a result of sequence of interactions, yes, there are options. There are some times where, you're going to get the payment method, it'll be pay by credit card, right? You can draw a second sequence diagram for pay by cash. You could, or you can do something like this with a simple if else. And that's all you're seeing. And that's another way to do this when you have a literal if else. So with this one, you have pay by credit card, and then you have a confirmed by the pay by credit card or pay by cash. And so it works out either way. But it's a simple if statement. You have the condition in the brackets. Same basic idea, except we're going to illuminate it into dashed lines. This dashed line very clearly says authorization okay or authorization fail. In the authorization okay, we get an authorization, we get a patient info. If not, we get an error, no access. Here's another example. It is a little broken, so I'm not going to go into too much detail. There's no if statements, but what you're seeing here is another alt. And this alt is, instead of being authorization okay or authorization fail, this is the same basic thing, Medcare DB and authorization. That's what Medcare is here. But this is an alt as well. And so you're going to log in, you're going to get an okay. Now, if you're going to send info, you're going to use these set of operations. If you're doing send summary, you're going to get this set of operations, and that's all it's saying. Okay. So when you send info, if the medical receptionist wishes to send info, they update the info with the patient info system, updates the PRS database. We do an authorization okay. We update the patient record system and we get an update okay. We get a message okay. We're done. Send summary, we'll update summary, summarize the UID. We do an authorization process. We create a summary. We update the PID, update okay. We get a message okay. Yay. Basically a same kind of thing. We're just seeing a different set of swim type lanes for a different operation. We tend not to do this too frequently in sequence diagramming because it's confusing. But when you have really simple things like this, maybe it makes sense. And so you do see it sometimes. You see this alt all the time if you have an if-else situation or failure, success, failure type thing. You rarely see it for different operations, but you could. Communication diagram describes the interactions of two or more things in the system that perform some behavior. It's any more one can do alone. This is the notion of synergy, by the way. That's the definition of synergy. Describes the interactions of two or more systems that participate in a synergy. Anyway, show the same information in a sequence diagram, but it may be more difficult to read is a sequence diagram. So we'll write it as a communication diagram. It emphasizes the organization of objects, sure, but sequence diagrams are organized primarily as a this happens, then this happens, and this happens, and that happens. If you want to organize the objects in some way, communication diagrams may be easier, but they're essentially equivalent. We can draw the same information via communication diagram as a sequence diagram. It's just written or drawn differently. Here's the example of the student interface. You can see the initialized student. Then you see select dorm. Then you see select program. Then you see student complete. Same information, except we're going to identify the different areas. Now, there's no real reason for this to be identified this way, the organization of objects. So don't focus. If anybody asks you what the difference between sequence and diagram is, one emphasizes the sequence. One emphasizes the organization of objects, but that's only part of the picture. Okay, that is true, but that's only part of the picture. So with the communication diagrams, if you have a lot of back and forth among, say, the program and dorm for some reason, it gets really difficult to see in a sequence diagram because you're seeing lots of back and forth crossing over, right? It's easy in a sequence diagram if these don't overlap, right? So we update the PRS system, authorize here, we authorize back, then we go to the PRS, right? If we had to communicate with the PRS system over here multiple times as different parts of this operation, we can reorganize the way those are related, but it may not be obvious how to do that. So a communication diagram is a much better way to do that. If you have to overlap things, you can draw communication diagrams a little bit easier. Here's a more realistic example. You have a customer creates an order for checkout. We debit, we take a credit card payment, we contact the payment processor system for a reserve, we get a commit. Then we get a get total, calculate the total. We go, as we're doing that, we go and get the order item. We get the price, the number ordered. We get info for the item. We get info back to the order. Checkout page has the info and it goes and gets it. So it's not just the price. Okay. Sorry, I already screwed this up. So let me do it over again. Okay. So it goes one first, but how do we get one first? Two is where we pay. So one, we go and get the total. Create the order checkout, we got to get the total. One, we go get the total for each order item. You see that asterisk? That means we're going to do it for each order item on the order. As we do that, we're going to get the price given the number ordered. It's going to return. We're going to have an order total. We'll keep calculating the total. Once we're finished here, 1.2, we can return back to the debit. And that's when the credit card payment is going to be processed. We reserve and commit. It has a total. Bang. Once that happens, we go to display. Checkout page. Now we need to get the info from the order. The 3.1 get info gets each order item, and it's going to get info for each item, and it's going to return it back to the order in order to display it. Ta-da! Sorry, it was a little bit communicative, but this goes all the way from the order checkout to the item through the total process. Then it goes to credit card payment. Then it does the whole thing. Once we know we're going to display, it goes and gets actually the all rest of the information. Because this, if drawn as a communication diagram, the order checkout would have to communicate across the order item and order checkout page across the credit card payment for both of those. It's usually not considered a great ideal. And so it would just make a really nasty looking communication sequence diagram, but a communication diagram is pretty obvious to see. Once you remember how to actually draw the darn thing, it's easier to see. All right, so structure models. These display the organization of a system in terms of the components that make up the system and the relation. Structural models are all about how the system is structured. They may be static, which shows the structure of system design, or dynamic, which shows the organization of the system when it's executing. There's a very special case of structural model we'll talk about. We don't use it too often, but you'll see an example of it. We create structural models of a system when you're discussing and designing the system architecture. There is little reason to create a structural model in the requirements phase, almost none. Class diagram is the most common, but these are object-oriented system models to show the classes in a system and the associations between those classes. This is what you're familiar with. if you've gotten through at 150 and 250, this is what you've seen before. An object class can be thought of as a general definition of one kind of system object. An association is a link between classes that indicates there's some kind of relationship between these classes. We'll talk more about that as we go along. When developing models during the early stage of software engineering process, objects represent something in the real world, typically a patient, prescription, doctor, something. Some modeling thing that you're describing. And then you're going to simplify and abstract it away. So here's an example. You have a patient and you interact with, and it's connected to a patient record. Note, there's no actual information here. You don't have any attributes and you don't have any methods for either one. But you can see you have a one-to-one association between a patient and a patient record. What do we need to know about a patient? What do we need to have in the patient record? We can start to break those down. But these are associations between classes. These are not actually showing the classes. But a patient might have one-to-many to one general practitioner. So each general practitioner has many patients. But each patient may only have one general practitioner. A patient may be diagnosed with a condition. One condition may be diagnosed to many patients. A consultant, a patient is referred to a consultant, but once we refer to a consultant, you have one consultant, they may handle multiple patients. Consultation, a doctor runs a consultation. 1 to 4 doctors are involved. They may have many consultations. Patient attends a consultation. One patient may have multiple consultations. One consultation may be for one patient. Consultation, in the process, we just prescribe medication. We may describe more than one medication. The medication may be described more than one consultation, or a treatment, same idea. Right? These are just about associations. One of the things we think about when we think about associations here in this process of thinking about associations only is we think of one to many, many to many, and many to one. And what do you mean by that? What are the number? How many different patients can a consultant have? Does each patient have multiple consultants? What about consultations? How many doctors are at each consultation? How many consultations does each doctor have? It's a way of breaking that down into a way of thinking about it that allows you to make some sense of the interactions. So here's the consultation class in a little bit more detail. You can see it has a consultation title. This is going to be the eventual name of the class. There are several ways of writing this that gives us more information about what the consultation is. Is it an abstract class, those type of things? We don't care about that. But in a consultation, we have attributes and then methods. The attributes are doctors. Now we look back at the consultation here. You can see you can have up to 4 doctors. So it might have an array of doctors. I might have a linked list of doctors, whatever. We have a date, a time, right? A clinic, a reason, medication prescribed, treatment prescribed, right? We're going to connect these things. The consultation is going to remember the medication or the treatment. Then you might have notes and a transcript of the consultation, what happened during the consultation and so forth. Methods, you might have you might have prescribe, you might have record notes, or you might have transcribe. Transcripts, by the way, when we think of voice notes, think of it like a recording, and then transcripts just being a written out part of the it's not that interesting, but that could be what it is. Not that interesting. Generalization is an everyday technique that we use to manage complexity. Rather than learn the detailed characteristics of every entity, we can place these entities in more general classes like animals, cars, houses, and learn the characteristics of these classes. It allows us to infer that different members have some common characteristics. Now, if you think we're not talking about inheritance, you're lying, right? This is absolutely inheritance, the inheritance process. That's what this is. In modeling systems, it's often useful to examine the classes to see if there's scope for generalization. This allows us to increase our reuse, but as well as simplify and create mechanisms for us to add things in later that we didn't originally think of. Changes are proposed. You don't have to look at all the classes in the system to see if they're effective. You can only look at the things that we need to. In object-oriented languages such as Java, generalization is generally implemented using the class inheritance mechanisms built into the language, right? Typically, that's the way it is. In generalization, the attributes and operations associated with high-level classes are also associated with the lower-level classes. We say that the lower-level classes are subclasses, and they inherit the attributes and operations from the superclass. These low-level classes then add more specific attributes and operations. So let's see an example, okay? For a doctor, you can have a hospital doctor or a general practitioner. Okay, no kidding. So doctor, might identify what kind of medicine he works in, blah, blah, blah. His age, where he got his MD, whatever. General practitioner may have just an address and a phone number, right? Hospital doctor, he's got the hospital, he's got the room number, the various things that we need to store about a hospital doctor. And why this is important is if something changes later on, is it the things that the doctor is supposed to know about or the things the general practitioner or the hospital doctor? By breaking this up, we make it more likely that the changes are relative to only one part of the system. It's building in change tolerance pretty quickly and early on, but it's also allowing for us to reuse the elements of doctor as much as we can. So a generalization hierarchy with detail, told you. Name, phone number, and email, register and deregister. Maybe you want to register with something or deregister with a patient, who knows. Hospital doctor has a staff number and a pager number. General practitioner may have a practice or address. Okay. Now, this is what I was talking about. If you change the way phone numbers work, change the way phone numbers implement, we don't have to do anything with doctor, hospital doctor, or general practitioner. All the changes should happen within the doctor class. If we change the way practices are managed, then we only need to look at general practitioners, right? That's kind of the benefit of the generalization hierarchy. But it does allow us to show how we actually want to develop them. And this is part of the design phase. We're going to develop pretty quickly. You're going to see we could develop a object named doctor, and then we can extend it. Hospital doctor could extend doctor, a general practitioner could extend doctor. We could definitely do that. Or we could create an abstract class doctor and so forth. This gives us some wiggle room to talk about and to hone the detail of our model further. But we don't usually get that far. But car and truck are specific examples of vehicles, and they inherit the general class vehicle. So a car might have a size, color, make, model, available, rate per day, rate per week, rate per mile, or style, right? This is a rental, right? Rent out, check in, service, add new. So vehicle has a size, color, make, model, available, rates per day, rate per week, and rate per mile. Okay, great. So what about a car is different than a vehicle? Style? Pretty much style. And you're like, wait, what? Yeah, that's it. It's literally just style. Because with a car, you could have a coupe, sedan, SUV, whatever. Okay? That type of thing. But that's the only thing. So with our car, we'd have very little to implement inside car since we get the size, color, make, model, availability, and the rate per day, rate per week, rate per mile, all from vehicle. We don't have to do anything special in there to have those same attributes. We just have to increment a single style attribute. Now, rent out, check in, service, add new. So if we're going to have a generic rent out, check in, service, and add new methods, in the car method, we have those same methods, but do we actually have to implement special versions of it? Maybe we do. Maybe in the rent out process, we just have to do the basics. Check-in process when, returning the car. We just have to do the basics. What condition is it in? Condition check, and so forth. Service, we just do all the service, right? But if it's a truck, maybe when we rent it out, we have to do different mechanisms for renting it out, maybe. You may have a CDL license that you have to show or whatever. Maybe there's a slightly different process. If there's a difference in the process, then we can go ahead and implement that in the subclass, right? So truck has a different rent out process where you have to check for a CDL license on certain cars, right? Also, keep in mind, truck has size, color, make, model available, just like everybody else does, rate per day, rate per week, rate per mile. But it also has a length, right? What kind of truck is it? Is it a 14-foot truck, 17-foot truck, 20-foot truck? And it's a four-wheel drive or manual shift, right? What kind of things about a truck do we need to know? Okay, those are specific to the vehicle. And if the rent out process is different for a car and their truck, we can implement that in the individual classes. And why do we do that? Let's suppose that the rate per week, the way we manage rate per week changes. We have to do that in vehicle, right? We only have to look at vehicle. Car and truck, bing, bang, boom, automatically handled. Great. What about make model? Same idea. What if we're affecting style? Then we don't look at vehicle, we look at car. What if we're affecting length? Then we look in truck and not car or vehicle. This again allows us to do kind of more interesting things. Now, suppose I'm going to rent scooters. Scooters have a size, color, make, mile, availability, rate per day, rate per mile. So I can just create a scooter class over here and then implement its specific functionality if necessary. This again is future-proofing as much as possible. Here's another class diagram. This one's a little bit more realistic. It's a little bit more about aggregation, okay? So a course has a department, right? CST 348 is from computer science department, right? Department has a name, it has a chair, and of course, maybe it has methods to add a department or view department. Course number, a course has a course number, course description, a number of credits, and a department number, okay? But we just said course has a department. Maybe the way we look up the department is by department number. I don't know. We can add a course, change a course, and find a course. Each course may have multiple textbooks. ISBN, textbook has ISBN, author, title, edition, publisher, whether it's required or not, add text, change text, and so forth. Now, each course may have assignments, right? Assignment number, assignment description, the points, due date, blah, blah, blah. Exam might have exam number, exam name, exam points, exam version, whatever. Okay. These are different types of aggregation. We can see the one to many, but we see this diamond, we see this other diamond, and look, why does it look that way? We'll talk about that in more detail as we go along. But aggregation model shows how classes that are collections are composed of other classes. For instance, an aggregation has a relationship. The whole object is composed of the sum of its parts. Okay? A department can exist without a course. Yes? A textbook can exist without a course. Yes? Right. Ta-da! And so these are more aggregation relationships. A course may have a department name, a department chair just being part of its course description, right? Instead of department number, it has the elements of a department. We could totally do that. We could have a department class and the course could have a department as part of it. We could totally do that. There's no doubt that we can do that. The textbook, we can do the same thing, but clearly it's an aggregation, right? The course has connections to these things, right? Maybe we tie off a number, maybe we tie off an ISBN here, but the course has these components, right? That's aggregation. Collection consists of a whole and its members. Members may change, but the whole retains its identity. So this is where we get a little bit different. It's not really shown here. And you go, wait, what do you mean? Right? So a student can mean a campus organization, right? You can have a list of students in a campus organization. In that scenario, you have students that could come and go like a list, and it won't really change much, okay? It's what we consider a weak association. Members may change, but the whole retains its identity. So even if every student left, the campus organization would still be the same campus organization, right? And if you think about a department course, right, no, you probably don't have a department have a list of courses and they can come and go. You could, that could be a total way to go, but likely in this one, the course is connected to it. Okay, actually that is absolutely aggregating that. A department has a list of courses. That is literally showing that. I apologize. It does show that. That's what the open arrow does. And then finally you have a composition. Composition is different. Composition, the whole has a responsibility for the parts. It's a much stronger relationship. If the whole is deleted, its parts will go away. So for example, we have a course and it has assignments and exams. If we get rid of the course, do we need the assignments and exams? No, because each one of those is for the course. So we consider that to be a composition model. Okay. And those are the different types of aggregation. Now, the has a relationship, just so we're aware, is similar to the composition, right? And you go, wait, what do you mean? So let's suppose we have a textbook. Yes? A course can have a textbook, and we have to list the textbook. But if we delete the course, we don't have to delete the textbook. It's not simply a list of textbooks, right? It's just the course connects the textbooks. A department has a list of courses, right? So that's more of the collection phase. But aggregation is similar to composition, except that if the whole is deleted, the parts don't need to be deleted. Yes. This is the aggregation. I don't care. Move along. We discussed interaction models, including purpose types, and they're important in modeling via use cases. We explained other interaction models including sequence and communication diagrams. The big thing about sequence and communication diagrams is yes, somebody's gonna read the book too closely, and they're gonna say it organizes the organization of classes or organization of the components, whereas the sequence model organizes a temporal thing. That's technically true, but the real reason we use sequence over communication diagrams, if it's easier to see it in a sequence diagram, you draw the sequence diagram. If it's easier to see whatever you're trying to see or communicate in a communication diagram, you do it in a communication diagram. Typically, when you have one part that has to communicate with a variety of other parts and the communication gets all over the place, the sequence is not usually very obvious, then a communication diagram is often easier to see. Whereas with sequence diagrams, if it's very relative, one thing interacts with one thing, then it interacts with another thing, and it interacts with a third thing. That's a little bit easier to see in a sequence diagram. But the answer to that question, when we use sequence or when we use communication diagrams, don't give me the organization of the things. That's actually bad. What I want you to say is instead, they're relatively equivalent. However, if it's easier to see it in a sequence diagram than a communication diagram, or easier to convey in a sequence diagram than a communication diagram, we use a sequence diagram. If it's easier to convey in a communication diagram, we do it in a communication diagram. That's the real answer to the question. You know, organizing objects, never do we actually care that much because we can organize the sequence diagram in objects as well by just simply compressing things. So it's not, I don't love that answer, but the book uses that in detail. Then we talked about structural models. This is really thinking about class diagrams are your primary mechanism, and they're really simple. The difference is we have 3 or 4 types of things we have to care about. Number one, you have generalization, right? And generalization is absolutely inheritance. It works exactly like inheritance. One of the things we don't see very frequently, although it did show it, was the association systems. This is frequently used when we do database modeling. So rather than showing, the detail of each element, it's really showing the one-to-one relationship, how we're going to aggregate them together. And as a result of that, we can start to build into the objects the type of, for example, you see in the consultation, you have a list of doctors. You can see where we can get those aggregations together to make this make sense, right? And you don't frequently see generalization until you need to pull out some things like a consultant, general practitioner, and hospital doctor. Is this, are these things related? Can we reuse those things? And frequently we can, frequently maybe we can't. But that's when we start to think about where we can use them and so forth. But generalization is often very useful. It's inheritance. It is absolutely inheritance and is absolutely inheritance and polymorphism. And we're figuring out from that structural point of view, how do we build our classes in the most simplest way, right? If you think about aggregation, right? Right? Aggregation and composition, right? Aggregation, we typically have a hazard relationship where how do we actually put a textbook in a course? Well, the textbook exists on its own. It's likely its own database table. So what I'm going to do instead of copying all the information and having two sources of information, what I'm going to do is take some identifier from the textbook and put it in my course. Ta-da! Then we see that with the department number. We do the same thing when we have a weak responsibility, right? Not really. What we're actually having here is a connection from the department to the course number, but here there's a list of somewhere there's a list of courses in a department, right? We can add and remove them. That's the collection phase, right? We think about our doctor. Well, I'm trying to remember where the doctors were. Doctors, right? Medications prescribed. If we keep that as a list, that is both the collections aggregation. Whereas a composition, we might have that. Oops, I'm going too far. Yeah, as a composition, we might have the assignment be an actual full-on object element of the course, right? As an example. Because that way when the object is deleted, so is the assignment as an example. So it's really just defining different ways to put these things together in a way that makes sense. And we can actually, as designers, we can constantly rework these, get details and get more details. And no doubt, we can also talk about what do we need to know when we add a course. What do we need to know when we're changing a course? What do we need to do when we find a course, right? All these things we can actually use and get more and more detail, like what's an ISBN? Well, in my case, it's going to be a number, right? It's going to be a 13-digit string number, right? As an example. Author is going to be a string. We could break this into further and further detail and work our way through from a high-level design to a relatively low-level design that someone could actually implement, right? And that's what we do when we talk about explaining relationships and class diagrams. We're doing that to show how you would actually go about building the actual system. And that is that. If you have any questions, please make sure you ask. Keeping these relatively short so that we can, the recording can be relatively short. But if you have any questions, please make sure to email me. If you don't understand class diagrams, you don't understand this process, you don't understand that process, you know, part of it is you do need to review a little bit of the stuff you did in 150 and 250. I don't go in the same level of detail as as they do in 150 and 250. I do, however, go in enough detail so that you can actually follow along. Also, I want to show you one other thing. Yes. So when you're showing inheritance and you're showing it is a relationship, you see the line and it's got an open square. That is showing the inheritance relationship. It is different from these guys. These guys are not showing inheritance. These are showing the aggregation process. Just as a reminder. So go back and review your class diagrams from 150 and 250 if you need to. I can work over an example when you see me again in class. What have you. The interaction models, sequence and communication diagrams are a little less maybe obvious, but they should be relatively straightforward given that their use is largely focused on how two things interact together to do the work they need to do. Most of the time we're doing these things, we actually ask what information is necessary where, what do we need to do to get a total? What do we need to do to this? We call the order, and then you go for each item in the order and so forth, right? You can break it down into what's needed where and go from a high level point of view to a much lower, more detailed description that you can use to build other things. Okay. And it also simplifies what we mean by interaction, especially when we're talking with humans. Yeah, but like I said, if you have any other questions, please make sure you ask them. This is recording for 10-8. There's another one, 10-10 coming up as well. All right, thank you. Bye.